Everyone, I'm Eduardo Pena,
I'm Samuel Morris.
and today we'll show you how to attack algorithms, brute force, and backtracking handle the NP complete tree coloring problem, and what we learned from testing them as well. This project has a simple question: can a small search streak turn an exponential problem into something fast enough for everyday graph? And to find out, we wrote both algorithms in C++ language, and then we then timed them on 16 graph ranging from 5 to 15 vertices, and then we compare the memory use. Everything will show you all the code, data, and results come from that process. Here's the problem statement. Given an undirected graph G with vertex set B and edge set E, can we color every vertex with at most three colors so that no edge connects two vertices of the same color? If we can do it, we output the colors. If no, we say it's impossible. And because the three coloring it's NP complete, the worst case running time for any set algorithm is exponential. Here we have the algorithms. First is the brute force, which is a straightforward. We generate every one of the three two-end color combinations. For each combination, we assign colors to all vertices, then scan two times the size of E edges to check validity. That gives us a time complexity of Beagle of two times the size of E plus N times 3 to the N, and a space of Beagle of N plus 2E. And then we have the backtracking um, algorithm. This one pretty much works differently. We color one vertex at a time, and after trying a color, we immediately test it against its color's neighbors. If it crashes, we back up and try the next color. That means it was the same color. For this one, the worst time is still 3 to the end. But in practice, the search tree collapses because most branches fall early. Those are the two methods that we will like Sam will show you next and how we build and test them.
Okay, so for the implementations, both the brute force algorithm and the backtracking algorithm were wrapped up into the same graph class. So they use the same storage and size complexity. So we used an adjacency list for storing the edges. You can see that in the code on the right as m underscore adjacent, which in C++ is a vector of ints. Each edge is represented as an integer. So for example, if you addressed m adjacency of 0, 1, you would get the first node's second edge that it connects to. And then we store the colors inside a simple vector of integers, which is m underscore colors. So when we get the data, we load it into this graph class, and then you can call brute force or backtracking on the same data without needing to do any extra work. Then for the implementations, the top function on the right is the certifier algorithm called valid. So this just checks if the graph and the colors that are stored in the graph are a valid three coloring. So to do this, the outer loop just iterates through all of the nodes. And obviously, if one of the nodes has no color, the algorithm did not execute and it is not valid. Otherwise, it goes through all of the edges for that node. If any of those edges match the color of that node, then you're connecting two nodes with the same color, which is not allowed, and thus the graph is invalid. So we return false. And then if you get through all of that without returning false, then the graph is valid and you return true. The brute force algorithm is in the brute force code on the right. So this is generating all 3 to the n combinations of colors. And if we hit a color that is valid, we will stop the algorithm. So by chance, You could get it right in O of 1 if the first combination is correct, or it could go through every single color combination to try and find a correct solution. So the outer loop iterates directly through from 0 to 3 to the n to generate all the color combinations. The inner loop iterates through every single node, and inside that inner for loop is some logic to basically convert the index of the outer loop into a system that allows us to count base 3 so that we can set the colors for every single combination inside of the color array. After we've created the combination with the inner for loop, we check using the certifier algorithm to see if the algorithm has produced a result that is valid. If it does, we return it. If not, we keep going through until we find one. So this has an O of 2 plus n plus 2 to the e times 3 to the n, because obviously the outer for loop is iterating 3 to the n times. And then the two inner ones, one is going through 2 times the edges and all the nodes, and then the valid function goes through all of the nodes again. But those are sequential, so the second one can be ignored. Then for the backtracking algorithm. For backtracking, we use recursion. So the top function is the backtracking function you call, which will just start at node 0 and use the backtracking helper to iterate through the recursion. So we start with node 0 of color 0, calling the backtracking helper. So each call of this backtracking helper will first check if the node is valid in a valid range. So if it's greater than, if you're at the end of the loop, it just returns true if you're past the node count. Then we check the colors of the surrounding nodes, and if the color you're trying to choose is already touching you, you cannot choose that color, so you return false. If the color is valid and you get through that check, then we set the node color to that color, and then we start checking the nodes after that one. So the if statement there will check the next node at color 0. If that fails, the next node at color 1. If that fails, the next node at color 2. If one of those works, then we return true, and that will, recurse up to prove that we have a correct algorithm. But if all 3 of those fail, then we undo the color, setting it to -1, and we return false. So that is the backtracking part of the algorithm. If you fail, we go back up a level, which will then try the other colors for the previous level. Instead of using for loops for this, since we used only 3 colors and we're not using the applicable K coloring algorithm, we simply used or short circuiting to iterate through all of the options instead of a for loop, because it's faster and it's pretty easy to look at. We also added the ability to visualize the graphs. This makes it easier to debug, and it also creates a more fun visualization of the problem. So we use the Bridges Web API, which basically we insert all the nodes and edges and their connections and colors into a thing, and it generates all of the graphs for us. So on the left is one of the examples using a Peterson graph, which is a typical graph used in the 3 coloring problem with 10 nodes and 15 edges. It's a little hard to see the edges between them because there's 2, as the Bridges API does not support undirected graphs. So it has one node going from one to the other, so 2 edges per node. But that also does better visualize the space complexity of our algorithm. And then on the right is just another example graph with 8 nodes and 10 edges showing the output of the program. So next, the performance analysis. The testing setup for the runtime. So we attached with our project a tests.txt file. This is where the program gets all the data for the graphs. So, at the start of the file, it tells you how many tests there are, and then each test will list off the number of nodes, the number of edges, and then all the node edge pairs. There are 16 tests included with our file. We ran some test graphs with n values ranging from 5 to 15. Anything higher than 15, 16 through 19 were decently performative, but once you get to 20 and past, the brute force algorithm becomes so slow that it's hard to test. So we stopped at 15. And then we timed each algorithmic run using SCD Chrono to capture the time before and after, and then obviously the subtraction is the runtime. For testing memory, memory usage was analyzed using Valgrind for each test case. This analyzes the entire memory of the program, so we would call the program with one specific test case instead of all of them, and then we just manually recorded the data for that. These values are obviously very large because it's the entire memory output of the program. So we use the relative memory values in our graphs, which is based on the difference between each test run and the test run with the lowest memory usage. So the lowest memory usage test run will have a memory of 0, but then every test run after that is based on how much more memory is using with that end value. So these are our results. The first one is for the brute force algorithm. So we're comparing the time complexity of O of 2 to the E plus N times 3 to the N, and the results, which were timed in nanoseconds. So the axis on the left side is the nanoseconds for the time, and then the right side is kind of just, there's no units for it. So, but we separated the axes, you can see the shapes better without comparing the magnitudes. So as you can see in the brute force, the growth rates are roughly equivalent. The algorithm performs as expected and is almost always near the worst case time complexity because there is nothing pruning the branches or doing any optimizations on that front. However, on the bottom, the backtracking results are very different. So it has the same time complexity as the brute force algorithm, but as you can see in the graph, the growth rate of the actual time that we observed is almost constant, excluding the outlier at 13, which is just unlucky due to the way the graph is created. But that also highlights the point that although this algorithm may be faster than the brute force, most of the time it, once again, can still be 3 to the n and go through every combination of the graph. But in general, this shows that the pruning using the backtracking method is much more effective than the brute force algorithm. And then memory results. So our theoretical space complexity is n plus 2 to the e because we're storing 2 edges for every node, and then we're storing 1 color for every node. We're storing all the edges twice because each node stores the one that it's connected to. So on the left, you can see the relative bytes of the memory used by the program, and on the right, we also have the n plus 2 to the e. So as you can see, the graphs are roughly correlated to each other. They're very close, and they get closer as n increases. This makes sense because we are exactly allocating n plus 2 to the e. There's nothing really changing that from each run.
Now some strengths, weaknesses, and improvements. As Samuel said, we saw a lot of improvement for the backtracking speed up on our tests. When we test the graph, the backtracking finish in microseconds. Will the brute force talk up to like I think it was like 144 microseconds around. So it's a big difference. We also saw that there was some consistent on the memory used because even on the peak overhead, it always stayed below 1K bytes across all the cases. So there wasn't any problem about the memory use, more about the CPU. And then we also really good point was the visual validation. The bridges output let us verify every value like three coloring by eye, which is really important when debugging and seeing the results. And then some weaknesses, exponential worst case remain because a carefully craft graph can still force the full 3 2n search tree and pretty much wipe up all the speed advantage. And then the recursion depth, because the backtracking recursive calls grow linearly with n, a very large graph could hit the stack limit. And then on the brute force, it's impractical because even with small graph, brute force explodes quickly and it's only useful as a baseline. Some improvement will be the highest degree first, since this one cuts average runtime even farther. It moves the hardest vertex to the top and it triggers the pruning sooner. We also have the this one degree of saturation ordering, which is like the next. It picks the vertex with the fewest legal colors left, and a quick addition that will let us like solve the graph roughly twice as large before the runtime spike. Some takeaways. First, the time complexity isn't everything. The two algorithms can share the same big O label and still behave very differently in practice. Second, backtracking crush brute force on every graph we try, proving that early pruning pays off. And then finally, small design choices matter. Like one line that reorders that vertices save us 4 orders of magnitude of runtime. That pretty much will wrap up the project. Thank you for listening.
Stop.